Thank you. Yes, believe me, folks, this is the last talk for today, so please bear with me for a few more minutes. What is this talk about? Yesterday in the banquet fun session, we heard a radical proposal to reduce cellular latencies by moving mobile devices inside data centers. Today, in this talk, I will present a more acceptable solution to reduce web latencies in cellular. Needless to say, performance of websites is important. Many studies have shown that faster websites have low attrition rates. A study from Akamai has found 57% of mobile users can tolerate fewer than 3 seconds of page load times before abandoning the site. Another study also shows faster websites make more money. Amazon says every 100 milliseconds delay could cost them 1% in sales. Every 1 second could translate $1.6 billion in their annual sales. Thus, reducing web latencies is very important. But what does the performance of web access over cellular look like today? Our measurements of top pages show web access over cellular is 6 orders of magnitude slower than wired. Why is that? This is because the page load process leads to lots of HTTP requests and responses that go in the high RTT last mile. Cellular, web as an application is latency bound, but then there are proposals, recent proposals, like the HTTP2 protocol that allows multiplexing of requests. However, in modern web pages, you have lots of small objects which are fetched from many domains, and also these web pages have inherent dependencies that prevent the client from requesting these objects in one shot. An example of such dependency is you might have to fetch the main HTML from the server and start parsing the HTML before even knowing what objects to fetch. Another dependency is you need to execute JavaScript code in the client to know what images to show for a client. Now, there is a tremendous interest in moving execution of browsing functionality to the cloud. The idea is to use a proxy that can execute browsing functionality for a client to quickly identify and fetch objects and push them to the client, thereby hiding the network latencies. Now, one might wonder, why do you need to execute in the proxy in order to just push objects? As I told before, web pages are becoming increasingly personalized. For example, you need to execute JavaScript to even know what objects to show for a client. Our study shows over 30% of pages have over 50% of objects which are not common across users. Thus, there are lots of these proxy-based execution proposals which have tremendous potential in lowering web latencies. But a key challenge with such proposals is the scalability of the proxy, which must execute the code for millions of users. To solve this problem, we first need to know where is the bottleneck. Unlike traditional web proxies, which are designed inherently to saturate the network, our measurements show execution-based proxies, the bottleneck quickly shifts to compute. Our measurements indicate that you need approximately 500 high-end servers to support execution for 1 million users. This translates to approximately $2.5 million in CapEx alone, assuming $5,000 per server. It's not cheap. Thus, reducing proxy compute is very critical. Now, if you look at what dominates the compute overhead in the proxy, our measurements indicate, again, that JavaScript execution in the proxy accounts for about 80% of the active compute time for a median page. So our contributions, this is the first work to scale execution-based web proxies. We developed a technique called Whittling to eliminate code not needed for object fetches. And we designed a system called NutShell, which incorporates Whittling. Some of our key results are NutShell can support 27% more user requests per second than prior execution-based proxies. And NutShell provides these scaling benefits while preserving or sometimes enhancing the latency savings. And whittling as a technique is computationally efficient. In other words, once you compute the whittle code, you can reuse across users and over time. So the outline of the further slides is, first I'll give an overview of existing execution-based approaches. I'll describe our system and end with evaluation results. The existing proxy-based execution approaches can be broadly classified as two classes. One is redundant execution, other is non-redundant execution. Note that both these approaches have potential to lower web latencies. But in what does non-redundant execution mean? In these approaches, you offload the client browsing functionality fully or partially to a proxy in the cloud. While approaches that fully offload browsing functionality to the cloud can hurt client performance during interaction, the approaches that offload partially to the cloud have to deal with complex state management when you want to migrate the execution back to the client. So another interesting class of approach is redundant execution, where the design is pretty simple. As the name states, the execution happens both in the proxy and in the client. The proxy execution is only to quickly identify objects and push them, while the client executes again, normally like a traditional browser. This approach, the design is pretty simple, and it minimizes the network round trips. Thus, this approach provides the best of both worlds. Since redundant execution provides us an opportunity to solve the scaling challenge, we exploit this opportunity to solve the problem. Why did we choose redundant execution? As I shown before, redundant execution reduces network delays that dominate page load time in cellular networks. For example, our study shows over 50% of the total page load time can be attributed to network delays in cellular for 53% of the pages. So in this redundant execution context, how can you reduce compute? I've been telling this multiple times. The proxy execution in redundant approach is primarily to identify objects to fetch, and client executes again normally. So the key idea is pretty straightforward. It should come to your mind. In the proxy, you can just execute code only needed for object fetches and skip other code. Now, is this idea feasible? Here is an example JavaScript from a top page. There are two functions. The dotted box is a function which is responsible to initialize some page GUI-related components, and the bottom box, the code is responsible to fetch some 3 images and show randomly on the components. As you can see, there is no dependency between the UI-related code and the image fetch-related code, and thus you can drop the UI-related code in the proxy. How can you automatically now find code to drop, or code that you need to drop at the proxy? In programming languages terminology, this is called backward slice of the code responsible for object fetches. So static JavaScript slicing is well studied in programming languages. There are lots of tools that exist. But generally, JavaScript slicing is considered as a very hard problem because the language is a very dynamic language. Also, the traditional concern with slicing is the slice has to be very accurate. You cannot miss any dependent code because the application is software debugging. So traditional slicing tends to be conservative. What do I mean by that? Here is an example of a code, the original code, where there are 5 functions, A, B, C, D, E. The blue functions are not part of the slice, and the green functions are part of the slice. Now, because the language is dynamic, you take a conservative approach, and the slice ends up like this. You have all functions as green. In contrast, our application is slicing, which happens only in the redundant proxy execution. So the key insight is the slice need not be accurate. We take the same example here. Say the slice ends up like this, where you have more functions, which is 4 functions in the blue box, which means the proxy is dropping some relevant code. This means the proxy is not going to push some objects, but because the client is going to do another full execution again, it is going to fetch these objects from the server. This ensures correctness of the page. Thus, we exploit this degree of freedom in our solution. Let's look at what a Whittling technique does. It does 2 executions. One is a full execution of the JavaScript code. Another is a partial execution, where we turn off a particular code block. We compare the output from both these executions. Here, the output means the objects fetched. If the objects fetched match, then you can whittle the code that was turned off. If the objects fetched don't match, you cannot whittle. A natural question is, at what granularity do we need to do this testing? You can take a coarse-grained approach and test an entire JS file, but this gives minimal benefits, because if you imagine, even if a single function in the file is responsible for object fetches, you would say the whole file cannot be dropped. On the other hand, you can do more fine-grained testing of individual statements, but that adds a lot of overhead. So in our work, in our solution, we take a middle ground where we test individual functions. Note that we turn off all invocations of the functions, so this is a bit conservative, and we'll see more results if we are a bit more aggressive. While incorporating Whittling in an end-to-end system, we address a bunch of system design issues. I'll briefly go over these due to lack of time. The first concern is it's time-consuming to test all functions. There are hundreds and thousands of JavaScript functions in web pages. When we profile the JavaScript execution of the top 100 pages using Chrome V8 Profiler, we found 20% of the top functions contribute to 80% of the total execution time. So the key insight is you just have to test these heavy-hitting functions to get most benefits. A next issue is function dependencies that you see in real web pages. What do I mean by that? If you individually test functions, you can safely whittle them because you don't miss any objects. But if you turn them off together, you miss some objects. What can cause this dependency? One example is redundant code paths. There are two functions, f1 and f2, which is responsible for initializing a jQuery library that is needed to fetch objects. Now, if you test these functions individually, the other code path will initialize it, and everything is fine. But if you turn them off together, then you miss some objects. There are lots of such dependencies, and we take an empirical approach in our study. And the question now is, can you find the optimal set of independent functions to whittle? Because it's time-consuming, in our work, we propose a greedy whittling algorithm. Please refer to our paper for the details. Final question is, it is very time-consuming to whittle at every page load. So to understand how stable is JavaScript content across time, we conducted a longitudinal study where we recorded the pages every hour, and then we whittled the JavaScript code, which was recorded at t equal to 0, applied the whittled code for t equal to 3. And the whittled code at t equal to 0 is able to fetch all the objects at t equal to 3. One might think that is because web pages are stable, but we verified, and the insight here is objects in a page do change over time, but the code is relatively stable that you're able to reuse the whittle learned over 3-hour window. To give an idea of the overhead, whittling has a one-time overhead of 213 seconds on an average, and it gets amortized over a 3-hour window. There is a prototype implementation. Please refer to the paper for details. We evaluate NutShell along two angles. First, how much scaling benefits does it provide? What is the impact on client latency savings? Our test set consists of 100 Alexa top mobile pages. We use recorded versions of the pages for repeatability of experiments. The scaling setup consists of a proxy, which runs at 100% CPU when you compare two schemes, so that the workload remains same. How do we achieve that? We have many clients simultaneously requesting the same page through many instances of the proxy. And we also scale the server so that the proxy to the server links is not a bottleneck. And the client requests the same page sequentially. Now, the workload is the same across both these schemes. And if you compare the total times taken to serve all these requests, because you cut work in NutShell, you'll be able to get lower time. This graph here presents the increase in user requests per second for individual pages. The x-axis shows the pages sorted by their popularity, and y-axis is the result. If you look at the first bar, it's for page rank 1, and you see about 60% increase in user requests per second with NutShell. Note that this includes all the other overheads in the proxy, like HTML, CSS, and networking, because we are not optimizing HTML, CSS. Now, in a proxy, you'll get a mix of pages with different popularities. So we compute an overall weighted average based on different models, and we see 27% overall improvement. Finally, these scaling benefits do correlate to the JavaScript compute savings that we see in the proxy. We see a speed up in JavaScript compute of 1.33x, and we get good scaling benefits for pages which are heavy on JavaScript. Example, in Facebook, we reduce 50% of JavaScript compute in the proxy. That translates to 43% in user requests per second. The last result, we compare the impact of NutShell on latency, the client latency savings. We use a lightly loaded proxy as it is reasonable. The client goes over live LTE to request one page, one at a time through these proxies, and we do multiple runs for statistical significance. We compare NutShell to a baseline speedy proxy, which is HTTP2 now, and we see 1.5x speed up for a median page. And this is because in speedy, the dependency resolution happens on the client, whereas here the proxy does it. We also compare NutShell to a lightweight proxy, which pushes only a subset of objects which are embedded in the main HTML. There is no JavaScript execution in this scheme. This is similar to HTTP2 L1 push. And we see about 1.24x speed up for a median page. This is because the proxy is able to push all objects and thus benefits in cellular networks. And compared to a redundant execution scheme, we get better benefits for 15% of the top pages. This is because you reduce some work at the proxy that leads to pushing objects earlier. Note that these benefits also hold for other metrics. We also did a user study. I'll skip this. And this is the related work comparing other solutions. I'll skip this for time. To conclude, NutShell is the first work to scale execution-based proxies. We automatically identify JavaScript code only needed for object fetches in the proxy. NutShell improves the scalability, which it improves by 27%, which means you need 27% less servers. It provides lower latency compared to Redx. Thank you, and I'm happy to take questions.